Hi, I'm Chris Brown, and this is part 1.9a from an introduction to axiomatic design. We're going to be talking about the design matrix now for the next few minutes, and in part 1.9b we'll be talking about its manipulation. So the design matrix, this is for testing for axiom 1 and avoiding what we call imaginary complexity. So part of the rationale for this is it will avoid costly, time-consuming iterations. Well, costly and time-consuming iterations. It'll keep the design adjustable and controllable. It'll help us to avoid unintended consequences. It avoids, or it involves a formal mapping process from one domain to another. So we're going to take a look at how the DPs influence the FRs, or how the PVs influence the DPs. First, let's talk about imaginary complexity. So when we have an existing design, it may have what we're going to call a quasi-coupled matrix, or a coupled matrix, and the order of adjustment of the DPs in order to satisfy the FRs without iteration is not known. Now we'll be seeing more about this as we develop this concept. And so we adjust an FR to get a one DP, or we adjust a DP to get one FR within tolerance, and then we find that another FR is out of tolerance. We adjust that DP, and that takes another FR out of tolerance. So we have to iterate to get to a solution, and it may not converge. So if we rearrange the matrix, though, we may be able to see the correct order, and there may be an order for adjusting the DPs so that we don't have to iterate on the FRs. And so in this case, we have what's called imaginary complexity until we can find out the right order. Right, so we can take a look at this as a kind of matrix equation. So how do we get from a DP to an FR? So the FRs are equal to some design matrix A times the DPs. So this design matrix is essentially what mathematically transforms the DPs into the FRs. Now the FRs and the DPs are both column matrices. So here's an example of what this looks like for 3 FRs and 3 DPs. So we have a 3 by 3 design matrix, and that's represented by A's with 1, 1, 1, 2, and so forth. Of course, this isn't limited to just 3 FRs and 3 DPs. You could have any number. So matrix multiplication, which is what we're looking at, because the design matrix times the DPs gives us the FRs. Matrix multiplication represents a series of equations, which you should have seen in linear algebra. Now we're just looking at a limited case of this, so if you never took linear algebra, or you don't remember your linear algebra, don't worry, because we're going to review everything you need here. Now one of the things that makes this particular case easy is that in axiomatic design, the A matrix, or the design matrix, should always be square, and the FRs and the DPs will always be column matrices. So to multiply matrices, we take the rows of the first matrix, are multiplied element by the columns of the second matrix. And then the products are added. And so this is what it looks like. So if we take this for the 3 FR, 3 DP case, here we can see the different elements of the design matrix, A11, A12, A13, and so forth, and how they are modifying the DPs in order to achieve the FRs. And so it's easy to see a pattern. If we look down the column, we see it's all DP1s multiplied by the A11, A21, and A31. And then if we take a look across say FR1 equals, and in this case we've got A11, A12, A13 times each of the DPs. So we have an easy kind of obvious pattern to see there. Now sometimes we write the matrix like this, or the matrix multiplication, and then we sort of multiply down by the dp's and add across to get the FRs, and so this looks a little bit more clear. So here's, for example, where dp1 is going to fit in, multiplying all of the first column in the A matrix, or the design matrix, and becoming the first terms in these three equations that define the three FRs. Now, as we go, we're going to manipulate these matrices, and when we do it, the validity of these equations must be preserved. So what we're going to make use of, essentially, is some very simple mathematical properties to do this. Now, there are other ways to that this can, or other notations we can use to represent the same sort of thing. So here we can use this kind of subscript notation, which some of you may be familiar with, and there's something else too here. In order to get this to work out mathematically, later we'll take this up and we'll see how the elements of the A matrix are partial derivatives. What we're really looking at here is when we change a dp, how does that change an FR? And so the A matrix is full of all of the partial derivatives relating the FRs and the DPs. And we'll get more into this later. So if you're uncomfortable right now with some of the partial derivatives and how it's going to work, don't worry about it. We will look at it in detail when we get to it. For right now, we really don't need any calculus. We just need to know if the element of the A matrix is 0 or non-zero or close. And whenever an FR, particular FR, is changed by a particular DP, then that's an indication that that element of the A matrix is non-zero. And it will appear in an expression for that FR. And that's what the partial derivative is telling us. If the partial derivative is 0, that means that the FR doesn't change when that particular DP changes. So here's the design matrix, and so represented out to so as far as you would like to take it. And so now, what are these elements in the matrix? Now, there might just be a coefficient, just a simple multiplicative coefficient. But it might be something more complicated. It might be a more complicated mathematical operation. Or we might just understand there's a table or a graph that tells us what the DP is doing to the FR. Now, at one point, or at some point in the design, just to check to see if it's decoupled, we don't really need to know what it's doing, just as long as it's enough so that we have to worry about the influence. Now, one of the things that we've covered is the number of FRs should equal the number of DPs. So the design matrix has to be squared to satisfy axiom 1. So each FR needs its own DP, and that we've discussed before, and so the square matrix is one of the manifestations of this. So if you have more FRs than DPs, the design will be coupled because I won't be able to individually influence each FR. If there are more DPs, in this case I need to find more DPs, right, or reconsider, do I really need all those FRs? In the other case, where there's more DPs than FRs, then the design is redundant. It might also be coupled. And then we need to decide which DPs to vary and which to hold constant. So if I've got more than one way of changing an FR, I need to say, all right, well, which one do I want to use, and perhaps under which circumstances. Now, the best kind of matrix to have is uncoupled. It's a diagonal matrix, and that means that all of the off-diagonal terms are 0. So in this case, what we're representing mathematically is that each DP influences one and only one FR. so that I can change each dp only influencing the one fr, and any order of adjustment works fine because no influence of a dp will take some other fr out of adjustment, and we'll take a look at what that looks like right now. Now this, a triangular matrix, is workable, and this is a lower triangular matrix, so the upper triangle, the off-diagonal terms to the upper right, are all 0. So in this case there's a clear order of adjustment, only one order of adjustment when it is a full triangular matrix. And so we have to start with dp1, and we'll adjust dp1 so that fr1 is within tolerance. Now at the same time, I've done something to fr2, 3, 4, 5, and 6, and this may be undesirable. So I can adjust dp2 to fix fr2, and since element A12 is 0, dp2 has no influence on fr1, so fr1 will stay within tolerance as I adjust dp2. Now, adjusting dp2 so that fr2 is within tolerance could take FRs 3, 4, 5, and 6 out of tolerance. And then the same thing happens with dp3. I can use dp3 to put fr3 into tolerance at the same time, maybe taking 4, 5, and 6 out of tolerance, and so on, until I finally adjust fr6 with dp6, and dp6 doesn't influence any other FRs, and so finally I'll bring fr6 into tolerance. So, of course, we're showing this on a 6 by 6 matrix, but any size could work. So what we do after each zigzag is we develop the FRs and then select DPs that are going to fulfill those FRs. We take a look at the matrix and decide, is this DP going to influence any other FRs besides the one that it's chosen to fulfill? And if it does, then we have to put an X in that column. And so here you can see that DP1 is influencing FRs 2, 3, 4, and 5, but not FR6. So as you fill this in, and you take a look and say what FRs might it be influencing, you would like to naturally try to find DPs that don't influence other FRs besides the one they're intended to, but many times you cannot. So after each zigzag, you take a look at the design matrix. Now, for filling these in, we use an X to indicate that there's a relationship and an O to indicate there's a lack of one, or just a small one. So how do we do that? Well, sometimes there's a kind of scientific relationship, and we can know from fundamentals that the mass influences the force when we're having an acceleration, for example. And so then the presence of the relationship should be clear. Another way to do it is just to ask everybody in the room, lots of times when you're working on a design review, and see if you can build up a consensus. So you have a kind of democratic process. Another way is to do it experimentally and design an experiment to see what the influences might be. So I've alluded to the tolerances a few times. So it's possible that the variation that we might see in a DP in the use of this design won't be enough to take some FR out of tolerance. And then we would not use an X, we would use a 0. So if the DP is not enough to take it out, we use a 0. For example, if our FR is to achieve a certain gas mileage, and we want to achieve that within a functional tolerance of plus or minus, say, 1 mile per gallon, is the radio antenna going to be enough to influence this, and does the DP for the radio antenna have some impact on the FR for achieving the gas mileage? I don't know enough about aerodynamics to say if it would make the difference of 1 mile per gallon, maybe on some very high performance competition vehicle. But anyway, you get the point. So axiom 1 is to maintain the independence of the functional elements. And so the goal is to figure out how to make all of the off-diagonal elements in the design matrix 0 rather than x. So we can maybe we have to rearrange to get the diagonal elements in place, and that's something, the rearrangement we'll see in the next module. The off-diagonal 0 can be an expression of optimism at the other level, an attempt to maintain this, and a commitment to try to avoid coupling further down in the decomposition, but we won't know until we complete the decomposition. Alright, so that completes the first module on the design matrix, and in the next part we'll take a look at the manipulation of the design matrix. Syncing. 3, 2, 1, now. Hi, I'm Chris Brown, and this is part 1.9b of an introduction to axiomatic design, and we're looking at the manipulation of the design matrix. So how do we manipulate a design matrix, and why would we want to do this? Well, this helps us to decouple a quasi-coupled design and eliminate the imaginary complexity that we talked about in the previous module. We do it so that it preserves the validity of the equations, and we're using the commutative property of addition to do that. And you might remember that from linear algebra, this kind of manipulation. The commutative property of addition you might remember from junior high school or before. So adjusting the order to achieve what we call a decoupled design. Now, if we have a triangular matrix, it's called an uncoupled design, and if we have a diagonal matrix, it's called an uncoupled design, and a triangular matrix would be a decoupled design. So the order of adjustment of the DPs to influence the FRs can be changed according to rules, or these following rules, in order to get a triangular matrix. Now, so when we change the DPs, or when we change the order of the DPs, we need to move the corresponding column, and we change the FR order, we need to change the corresponding row. Let's see what that looks like. So here's one of the representations of the design matrix with the FRs and the DPs. So we move the DPs with a column. So here is a column with the DP, and then let's say we want to move that so that it's now to the right of DP3, and it would look like this. And actually I've also here switched, so I've switched DP1 and DP3 is what I've done. So I've exchanged the two, and we've kept their columns with them. So there's actually been two moves here, more than represented by the arrow. So it was a DP1, DP3 switch. Let's take a look at the FRs, moving the FRs with the rows. So if we move FR1 down here and do the FR1, FR3 switch, then we see that the rows move with the FRs and the columns essentially stay the same, although the order changes in the columns naturally. Alright, so here's an exercise that you can do. You can write out the design equations and then show that the equations, the validity of the equation is preserved using the commutative properties. So what we're trying to get is a triangular matrix, or a decoupled design, so that it looks like this, in this kind of representation. And so in this case, DP1 is influencing all the FRs, DP2 is influencing FR2 and FR3, and DP3 is only influencing FR3, so that we have a clear order of adjustment, DP1, DP2, DP3, in order to avoid iteration and putting all the FRs within tolerance. So here's what the design equations look like, then written out in the full form. So we can see that we can adjust DP1 to get FR1 where we want it, but this also influences FRs 2 and 3, and so forth. So, all right, here's some exercises. Can this design solution be adjusted without iterating? Now we can see a couple things here right away. One is that there are only 2 dp's for 3 FRs, so we know we have a problem. And so if we take a look, dp1 is influencing both FR1 and FR3. So if I get FR1 in tolerance and take FR3 out of tolerance, then I don't have an adjustment on the design because there's no way of bringing FR3 back in tolerance except with dp2, which, as we can see, also influences FR3. But then FR2 may come out of tolerance while adjusting dp2. And again, there's no guarantee that we can make these adjustments and that it'll work and the solution will actually converge even with iterating. Okay, so can this design solution be adjusted without iterating? And if so, what's the order of adjustment? Now we should be able to look at this and see it's an upper triangular matrix. And with a lower triangular matrix, since we went dp1, dp2, dp3, with an upper triangular matrix, it makes sense that maybe we should adjust dp3, then dp2, and then dp1. And indeed, we can see that that's the case because dp3 influences all the FRs and dp1 only influences FR1. And so we can use that 3-2-1 order on the dp adjustments to put all of the FRs in tolerance and fulfill all the FRs. So, what about this? Can we adjust the dp's? Is there some order that we can adjust the dp's? Now, with a 3x3, we could just try all of the possible orders. It wouldn't take that long. We can also use software for this, and there's some design software from axiomaticdesign.com that you can download there called Aclaro. In this case, though, I think you can see that it's going to be impossible to find any order of adjusting the dp's so that all of the FRs can be within tolerance, because every time we go to adjust one of the dp's to get the FR within tolerance, we're putting another FR out of tolerance. Alright, what about this case? Is this coupled or decoupled? We know it's not uncoupled because uncoupled would mean that all of the off-diagonal terms were 0. Now we have an interesting thing here. One of the diagonal terms is 0. Is there any way of rearranging this matrix so that we can get non-zero values on the diagonals? So I think you'll see that there's a clear problem here, that we've got no way of adjusting this without iterating again. Now, in this case, we have a lower triangular matrix, but one of the elements in the lower triangle is 0. So what would be the possible orders of adjustment here? And is there more than one? So again, with a 3x3, we could do this by trial and error. And we could see that there are 2 orders of adjustment. We could either start with dp1 or dp2 and then do the other one. The only thing we have to be sure of is that we do dp3 last. So here's one that looks a little more complicated. So how can this be rearranged to show that it can be adjusted without iteration? So let's take a more careful look. So if we move the dp's with the columns, so in this case we're going to exchange dp1 and dp2. So we note that the equations are unchanged. However, now are we any closer to an order of adjustment? So looking at the matrix, it looks like we could get this into a lower triangular matrix with one more adjustment. Let's see. So we can move the FRs now so that we will exchange, so that we will move FR1 down into the number 2 spot, FR2 down into number 3 and FR3 into the number 1. So we're just moving FR3 up, essentially. And then you can see that we have a lower triangular matrix, and again we have an extra 0 in the lower triangle, indicating that there might be 2 orders of adjustment. And in fact, as long as I do dp2 first, it doesn't matter if I do 1 or 3 next. So, just as I said, there's so if we do dp1 or dp2, dp1, dp3, we can adjust the FRs without iteration. So, for a full triangular matrix, there's only one order of adjustment to satisfy of the dp's, which will satisfy the FRs without iterating. All right, let's go back for a moment now, and in one of the earlier modules we talked about how all thought was about semantics, and semantics is essentially about symbol manipulating. So what we've done here with the design matrix and the FR and the DP column matrices is we've rendered the design problem to symbols. Then we can manipulate the symbols according to certain rules, and the quality of the design improves. In other words, we're able to show how to adjust the DPs without taking without having to iterate and getting all of the FRs within their functional tolerances. So we can make the order of adjustment of the DPs obvious, and non-productive iterations can be eliminated, and the adjustability of the design is maintained or achieved, and unintended consequences are avoided. So we've done what we've done with other kinds of engineering problems. We've rendered the problem into a mathematical form, then been able to solve it mathematically, and then see what happens from that. Now, as I mentioned before, there's software that can do the matrix manipulation, and that's available at axiomaticdesign.com. So here's an exercise. Can you figure out how you might be able to tell at a glance if decoupling is not possible? And are there some configurations where you can tell at a glance that there are multiple orders of adjustment of the DPs to fulfill the FRs? Okay. Thank you for your attention, and this ends the unit on matrix manipulation.